Hi guys, well we were talking about this very operation of scalar multiplication that was nothing but multiplying a given matrix by a scalar which produces a new matrix of the exact same order. So basically if you are given a matrix, because you have infinitely many scalars available with you, corresponding to each scalar you can get another matrix of the exact same order. So what did we study basically in the concept of the operation of scalar multiplication? That was multiplying a matrix by a scalar to produce another matrix of the exact same order. So here basically we said that A is a matrix which in compact form is represented like this if it is of order m cross n. Well, if I am saying that matrix A is represented like this in the compact form, this means that the arbitrary ijth element of matrix A is small aij. Yes, this means matrix A's ijth element is small aij. And this is true for every I varying from 1 to m and j varying from 1 to n. Is it understood? Now if A is given to be such a matrix, now this m cross n can be anything. M may be equal to n, m may be unequal to n, m may be less than n, m may be greater than n. So here whatever m cross n order is, I am saying if you take a scalar k, let k be any scalar, then what happens? If k is any scalar, then what happens is, basically if you multiply this k with the matrix A, you get another matrix Ka. Now multiplying a scalar with a matrix does not actually make sense. What does it stand for? When I say multiplying a scalar by a matrix, this means that multiply that scalar with this given matrix, which means that multiply each and every member of this matrix A by k. So aij is going to now become k times aij. That means if the ijth entry of matrix A is aij, then ijth entry of matrix Ka is k times aij. Isn't it? Because the order is exactly the same of A and K, that means the positions available with A and the positions available with Ka are exactly identical, and therefore I can say that the ijth member of Ka is k times aij, which means nothing but k times ijth member of A, and this is also true for all I varying from 1 to m and j varying from 1 to n. Is it understood? This is the concept of A and then corresponding Ka. You have just one matrix and one scalar to get this new matrix K times this matrix A. Because you have infinitely many scalars with you, with the help of one matrix and those infinitely many scalars, you can create infinitely many new matrices by multiplying those scalars with this given matrix. After understanding this entire concept of multiplying a scalar by a matrix to create new matrices of the exact same order, we had focused upon understanding certain properties of scalar multiplication. Scalar multiplication. Okay? Understanding certain properties of scalar multiplication. What are the properties of scalar multiplication? We had already revealed ourselves towards the first property, wherein I told you that in order to perform this very creation of the matrix Ka, you need a scalar k and you need a matrix A. So you need this scalar and you need this matrix. One matrix, one scalar is going to help you create a new matrix, which is going to be created by multiplying that scalar with the given matrix. Here I told you that if you take one scalar and take one matrix, this is one matrix. A plus B is one matrix. A and B are given to be of the exact same order, m cross n. A and B are of exact same order m cross n, therefore A plus B is again of order m cross n. A plus B is again of order m cross n. I am saying A and B are two matrices each of order m cross n. Then A plus B is first of all defined and is again a matrix of order m cross n. Now I am saying that A plus B is one single matrix, K is one single scalar. So I can talk about K times A plus B. This is going to be standing for multiplying the scalar K by the single matrix A plus B. Now this scalar K can also be multiplied with matrix A. That's not a problem. Why? Because A is a single matrix, K is a single scalar, so K times A is very much defined. Here I know that A is a matrix of order m cross n and therefore K times A. K times A, we know that if A is a matrix of order m cross n, then K times A is again a matrix of order m cross n. So this again K times A is of order m cross n. Exactly in a similar fashion, because A and B are of exact same order, even B is a matrix of order m cross n. So I can also talk about K times B. B is a single matrix, K is a single scalar, so K times B is very much defined and is known as multiplying the scalar K by the matrix B. As I said that B and A are of exact same order, therefore if A is of order m cross n, B is also of order m cross n. K times B is again therefore going to be a matrix of order m cross n. K times A is a matrix of order m cross n, K times B is a matrix of order m cross n, so clearly their addition is defined. Their addition is well defined. Their addition is going to be a matrix again of order m cross n. We know this. If one matrix is of order m cross n, second matrix is of order m cross n, then the addition of these two matrices is very much defined. The sum of these two matrices exist as a matrix whose order is exactly same as the order of these matrices, which is m cross n. Order is m cross n. Is it clear? Now this is a matrix of order m cross n, this itself is a matrix of order m cross n, this is a single matrix, this is a single matrix. Claim is that these two matrices are exactly equal to each other. For every scalar K and matrices A and B of exact same order. These are the prerequisites for this result to hold, like the hypothesis. So here once the claim has already been declared, we need to just show that not just for one or two examples like we dealt in the last class is this property true, but actually in general also this property holds very much true. How do we prove that? Heading towards the proof, I am going to take A and B, two matrices of exact same order m cross n, okay. So I am taking let A be represented by Aij m cross n. Basically I am taking matrix A to be a matrix of order m cross n, and I am taking matrix B as Bij again of order m cross n. A is a matrix of order m cross n, B is a matrix of order m cross n. Once these two things are settled, I am taking K is any scalar. K is any scalar. If I have to show that K times A plus B is equal to Ka plus Kb, K times A plus B is equal to Ka plus Kb, if I have to show, that means I have to show what? These are two matrices. To show two matrices are equal, I have to show that their orders are same. The moment their orders are same, the positions available in both the matrices are same. So the next step is to show that the elements sitting in the corresponding positions are also same. So I need to show two things, that order of K times A plus B is equal to the order of K times A plus K times B. This is not something we need to show because we have already verified here that LHS matrix is of order m cross n and RHS matrix is again of order m cross n. So order of these two matrices is exactly the same, and that is m cross n. Next thing to show is, once the first claim has already been shown, The next thing to show is that the elements sitting in respective positions in both these matrices are also same. Now see, when the orders of two matrices are same, the positions available in both the matrices are exactly same. So pick up any ijth position which is common. Obviously every position is common in these two matrices because the orders are same. Pick up any ijth position. I need to show that the elements sitting in these ijth positions are also same. So I need to show that in the LHS matrix, which is K times A plus B, in this matrix the ijth element, whatever is it, is equal to the ijth element of the RHS matrix. Is equal to the ijth member of the RHS matrix. Is it understood? So this is equal to this I have to show, and this I have to show for all I varying from 1 to m and j varying from 1 to n. So what we are going to do is we are going to pick up an arbitrary ijth position, and we are going to show that K times A plus B, in this matrix the member sitting at the ijth position is same as the member sitting at the ijth position in the matrix Ka plus Kb. Do not forget this concept. Just do not forget this concept that the ijth element in K times a matrix is K times the ijth element in that matrix. Keeping this in mind, let us focus upon the proof of the second part. Let us see how we are going to prove that. So here let's pick up the ijth member sitting at K times A plus B matrix. So if I consider that K times A plus B is the matrix, and of this matrix I am considering the ijth element. What is the ijth element of K times any matrix? It is K times the ijth element of that matrix. So it is equal to K times ijth element of the matrix A plus B. What is the ijth element of the sum matrix? It is the sum of the ijth elements of both the matrices. So here I have, what is A plus B matrice's ijth element? It is A's ijth element plus B's ijth element. See, at each and every step the older concepts are being revisited again and again, and that is only going to be done in this chapter. Again and again we would be needing the concepts which we have already done, like we have done the addition of matrices concept. It is being used and required in the scalar multiplication concept. So if that is not clear, you won't be able to proceed and come to this step, okay? So keep on revisiting your older concepts and get a thorough grip upon them. What is the ijth member of matrix A? Let's see. Here I have written matrix A in the compact form. The ijth element of matrix A is represented by small aij, and ijth member of matrix B is represented by small bij. So here I have matrix A's ijth element is small aij, matrix B's ijth element is small bij. Okay. Now the moment this is written, please understand that this is a real number, this is a real number, this is a real number, or you can also get them as complex numbers, that's not a problem, but they are numbers. You know that 2 times 7 plus 3 is 2 times 7 plus 2 times 3, because multiplication always distributes over addition in numbers. In numbers, multiplication always distributes over addition. You can see 7 plus 3 is 10, 10 into 2 is 20. And this is 7 into 2, 14, plus 3 into 2, 6, which is again 20. So you know that when there are numbers, then multiplication distributes over addition. Over here, K is a number, Aij is a number, Bij is a number, and it is, the situation is almost like the same. It is multiplication being allowed to distribute over addition or not. Because these are numbers, multiplication will very much distribute over addition, and you are going to eventually get, this is K into Aij plus K into Bij, K into Aij plus K into Bij. Okay? Now that we have this with us, K into Aij plus K into Bij, please understand what is this representing. Aij is the ijth member of matrix A. When I multiply it by K, it becomes the ijth member of Ka. So K times Aij is nothing but the ijth member of the matrix Ka. Similarly, Bij is the ijth member of matrix B. When I multiply it by the scalar k, it becomes the ijth member of the matrix KB. So this is KB's ijth member. Now see, I am adding the ijth member of one matrix with the ijth member of the other matrix. The answer is going to be nothing but the ijth member of their sum matrix. That is what is the definition. If I add ijth member of A with ijth member of B, I eventually get the ijth member of A plus B. So if I am adding ijth member of Ka with ijth member of Kb, I am actually getting the ijth member of Ka plus Kb. So this member is nothing but Ka plus Kb's ijth member. It is Ka plus Kb's ijth member. So what have you got? That ijth member of K times A plus B is same as ijth member of Ka plus Kb, and this ijth was an arbitrary position picked up from among these two matrices all positions, and therefore I can say that not just their orders are same, but the elements sitting in corresponding positions are also same, and therefore I can say that K times A plus B is equal to K times A plus K times B. So in the last class, that the example that we did, in that example we actually verified this property. It was not just true for that example, in fact it is true for every scalar k and for every two matrices A and B of exact same order. The moment this hypothesis is met, this property is going to definitely hold. There is no confusion about that. We were verifying it by an example, but actually it is always true with this hypothesis holding. Now that the first property is done, let's now focus our attention towards the next property, which is going to be our second property. Now in the second property also, please realize that we are studying properties of scalar multiplication. Now in the very concept of scalar multiplication, you are able to get new matrix, which is with the help of a scalar and with the help of a single matrix. You need one scalar and one matrix to get the new matrix. By the concept of multiplying the scalar with this given matrix, the new matrix is created of the exact same order. So don't forget this particular thing, the second property. Let's do it. We need one scalar and one matrix. Now see, I am saying K is a scalar, L is a scalar. If K is a scalar, L is a scalar, K is a real number, L is a real number, K plus L is also one real number, K into L is also one real number, or K plus L is also one complex number, if K and L are complex numbers, or even one is complex number, right? What I am trying to say is, with the help of two scalars, I can always get one scalar by adding them. Now this is one single scalar. K plus L is one single scalar and A is any matrix. So I can definitely talk about K plus L times A, because K plus L is individually going to be a single scalar, say M. So now I have one scalar M and one matrix A, so M times A is very much well defined. What else can I do is, with the help of K and my matrix A, I can create Ka. With the help of scalar L and matrix A, I can create La and then add both these. Why am I adding both these? Over here understand that the order of matrix A is M cross N, K plus L is just a scalar. So scalar, when it is multiplied by a matrix, the order does not change. So the order of K plus L times A is also M cross N. Now over here, if you see, as I said, A is a matrix of order M cross N. K times A is again a matrix of order M cross N. K times A is again a matrix of order M cross N. Exactly in a similar fashion, you know, over here also A is a matrix of order M cross N. Then L times A, L is a scalar. This is also a matrix of order M cross N. Now see, if K is a matrix of order M cross N, LA is a matrix of order M cross N, their addition is well defined, and the new matrix created, which is Ka plus LA, is again a matrix of order M cross N. Order M cross N. So you are seeing that the matrix on the left hand side is of order M cross N, matrix on the right hand side is of order M cross N. In fact, not just their orders are same, they completely are same for any two scalars K and L. For any two scalars K and L, and matrix A of order M cross N. in this regard, how do you try to show that this is true? See, first of all, let's take an example. If I take k to be say -2 and L to be say 3, let me take matrix A to be 2, 1, 0, 3, -1, 5. This is a matrix of order 2 cross 3, 2 rows and 3 columns. What is k plus L times A? Let's see. LHS. K plus L times A. K is -2. Let me not take this 3, let me take it as 4. -2 plus 4. K plus L is -2 plus 4 times A, which is 2 times A. Okay, which is what? 2 times 2, 1, 0, 3, -1, 5. What is this matrix? 2 times A is the matrix which is obtained by multiplying each entry of A by 2 respectively. So, this is again going to be a matrix of the exact same order. So, the 1/1th element will be 2 into 2, that is 4, then it will be 2 into 1, that is 2, 2 into 0 is 0, 2 into 3 is 6, 2 into -1 is -2, 2 into 5 is 10. So, this is your K plus L times A, this is your matrix. Then if you talk about RHS, it is K times A plus L times A. K is -2 times 2, 1, 0, 3, -1, 5. -2 times this plus L times L is 4, 4 times 2, 1, 0, 3, -1, 5. What is this? This happens to be -2 into 2 is -4, -2 into 1 is -2, -2 into 0 is 0, -2 into 3 is -6, -2 into -1 is 2, -2 into 5 is -10. Plus, you have this 4 into 2 is 8, 4 into 1 is 4, 4 into 0 is 0. And next you have 4 into 3 is 12, 4 into -1 is -4, 4 into 5 is 20. You can very easily see this is a matrix of order 2 cross 3, this is a matrix of order 2 cross 3, therefore they are conformable for addition. The moment I add them, I get again a new matrix of order 2 cross 3, and what is that? What does that turn out to be? Let's understand. What does that turn out to be? Well, I have Ka plus La is again a matrix of order 2 cross 3. 1/1th entry will be -4 plus 8, that is 8 minus 4, which is 4. 1/2th entry will be -2 plus 4, which is 4 minus 2, that is 2. 1/3th entry will be 0 plus 0, which is 0. So, you have 1/3th entry as 0. Then 2/1th entry will be -6 plus 12, 12 minus 6 is 6. So, you have 6 over here. Then you have 2/2th entry, 2 minus 4, that is 2 plus -4, which is -2. And then you have -10 plus 20, which is 10. So, what do you see? You observe that Ka plus La is this matrix, which is exact same copy of this matrix, which is K plus L times A. 4 2 0, 6 minus 2 10. Here also you have 4 2 0, 6 minus 2 10. Is it understood? And therefore, you have verified that K plus L times A is equal to Ka plus La. Is it understood? This happens to be your very next property, but it is not just true for this matrix A or this K or this L. It is actually true for any matrix A, any scalar K and any scalar L. Okay? At one moment, if you have a matrix A, you have scalar K, you have scalar L, then in general also you have this property very much holding to be true. Let's prove that. How do you say and declare that this is true? Over here, if we move ahead with the proof, how do I talk about this? I have A as this matrix Aij m cross n, and K and L are scalars. Okay, let me just tell you the drill. A is given to be matrix of order m cross n, K and L are given to be scalars. What can I say now is I basically have to show that K plus L times A is equal to K times A plus L times A. Both LHS and RHS are matrices. If I have to show two matrices are equal, that means I have to show their orders are same and the corresponding elements are same. So first of all, I have to show order of K plus L times A is same as order of Ka plus La. Now see, order of K plus L times A is m cross n, and order of Ka plus La is also m cross n. So this thing is already proved that okay, order of K plus L times A is always equal to the order of Ka plus La. So this one thing is done. Second thing is that the element sitting at each and every respective position is also same. So if you consider this matrix K plus L times A, in this matrix whatever element is sitting at the ijth position, same element should be sitting at the ijth position of Ka plus La matrix. Exactly same element should be sitting at the ijth position of Ka plus La. Is it understood? This is what I have to show, and this should be true for all I varying from 1 to m and j varying from 1 to n. Okay. So here the task for you is to pick up an ijth entry, find out what is the ijth element of K plus L times A, and see whether it is coming out to be equal to the ijth element of Ka plus La or not, and I am going to complete that with you in the next lecture. So I will see you then. Thank you.